Now, when I was a little boy, I used to read science books like this. It would tell you all about magnets, all about the weather. But really, when you read a book like this and you look at magnets, you learn nothing. It doesn't tell you anything. It's supposed to be science. But just learning the names of planets or reading through the book, how this works, or how something else works, doesn't really tell me anything. It leaves me feeling empty. Isn't it part of a bigger story? Why do magnets need to attract and repel? It doesn't tell you in the book. And in fact, I've never read a science book where it did tell you. So when I came to wagor, I wanted to start a science program that really told the whole story to the children. So that's what I want to tell you today. This is how we teach science in wagor. And it really isn't just learning about the names of planets and the names of anything you can imagine. It doesn't matter. A name is just a name. And it's not science. So what I'm going to do today is to start right at the beginning with what we do in grade 1. Now, it's never too young to start, because if you teach it in a nice simple way, the children do start to understand. And what we want them to see is that everything fits together, and it must fit together that way. Now, when I was a little boy, I used to read this book on physics. It's all about physics. It was my favourite book, and for 40 years I read all the mathematics, but really I still didn't understand what was it all about. And really this mathematics and the physics in the book are not what people do, it's what people find to be true. So Isaac Newton, who you all know, he didn't make the rules, he found the rules, and that is completely different. So, I'd like to start here with the Earth, because a long time ago there's no Earth. So the Earth must have come from somewhere, and it must have made itself. Now that means if you just have some dirt, just some dust out in space, inside the dust is something that can make places like this. And eventually, inside the dust must be everything to make oceans and mountains, volcanoes, air, and eventually living things, all by itself. Now, that seems very hard for us to understand. How can everything make itself from something like this? So here's the story. Everything is made of atoms. And in the beginning of time, there was just one atom, the hydrogen atom, which would just be something like this. They're electrical charges. They're not really things, not in the way that we think of things. Every time you look through the window, you will see there's no thing there. I can see right through it. But if I just have a large electrical charge, which is plus, and a small electrical charge, which is minus, everything will start to make itself. So there must be something inside here which will make things. And there's two natural forces, two things inside every atom, which are the forces that make things. The first force that we're going to look at, and this is what we look at in grade 1, is gravity. You should never look at magnetism by itself, because it's that partnership, that relationship between gravity and magnetism, which is the true force of creation. Now, you all know magnets have poles, north and south, which are different. Magnets attract and repel. That's what you learn in the science book, but does it really help you? No. what we're going to look at is how they are different and how they're the same and how they complement each other to make everything. The Earth looks like this. It's a sphere. The Sun looks like this. The Moon looks like this. The Jupiter looks like this. All the planets look like this. Now, that has perfect symmetry, and symmetry denotes meaning. There's a reason why everything is the same shape, and that's because gravity doesn't have poles, and it doesn't repel. If it doesn't have poles, it can only make this shape and nothing else. Now, the laws of physics are the same everywhere, throughout the whole universe. So when you read this book, we find these laws. It's not just something that happens on the Earth or something for people. It happens everywhere. Now I can demonstrate that by showing you these two pictures here of something on the Earth and something which is so big you can't even imagine how big it is. The human brain just can't imagine. But they're both the same shape for the same reason. Now that means that the laws of physics for the very big and things like this are all exactly the same. It always does the same thing. So if you want to understand something, you must understand from very basic principles. So gravity makes these shapes. It doesn't make anything else. It only makes big things because it's very, very small. It cannot be and must not be any bigger. We'll tell you why later. Now, we really want to look at the small things on the Earth, which make them self. A long time ago, the Earth would have just been a ball of fire. Well, out of that ball of fire, we have to get water and living things and all the things that you see outside, all the greenery, all the bacteria which are living on me, and eventually people. But let's start here with a new Earth. And I'm going to draw a timeline for you. Now we'll use the timeline quite a lot. It's very important to see how long it took and how long it takes for things to happen on non-human scales. That means for solar systems. Here, the Earth made itself by gravity. Now, gravity only makes spheres and big things. It can't make anything else. It's magnetism that makes everything else. Now, this is the real story of magnets, because magnets create all the small things. They make everything else, everything which is smaller than this shape. They make water, H2O. It's magnetism, electromagnetism, which sticks that together. Now that reaction between atoms is the driving force of everything that's small. It's because magnets have north and south, and they repel and attract, that you can make complicated things. And because magnetism is very strong, you can make small things. So if I could look down inside the table, for instance, I would find, looking at something like this, now it all looks very complicated, and it looks like a mess. It's not what I want if I put these together. They just put themselves together. But really, let's look at what happens when I put magnets together like this. I've got a very strong magnet here, and if I just put small magnets on here, it starts to make things by itself. It doesn't make a mess. It makes symmetrical shapes. And water looks pretty much like that. H2 and O. And there's no end to the number of shapes that you can make, but they are mathematical. And if I add some more, it keeps on making symmetrical shapes. Now that is very important, because if magnets didn't do that, then you couldn't have complex things, and you certainly couldn't have complexity of life. We're going to get onto complexity later. Complex things are very difficult for us to understand because it confuses us. But what's very important to understand is that complexity never takes complex steps. It only takes simple steps. So you need lots of time. Now, time is something that you do have lots of. Now, let's go over here and look at the timeline. Here's the Earth when it first made itself, 4.5 billion years ago. Life starts very, very quickly on the Earth here. It's very, very simple life, but it is life. And what I do in the school is to try and give the children a feel for what a living thing is. Now, to do that, we need to say what all living things have in common. Now, if I look here, I see life needs a cell full of water. It must be inside a small cell, and it must be water. That's the one thing that every living thing on the earth needs, and there are no exceptions. But why water? You all know you need to drink water every day, but nobody tells you why. There's no food in water, so why water? Well, if life is really made of small molecules, millions of them, which all need to find each other inside, they must be able to move. And because water is a solvent, if I put anything like sugar or salt into water, I can see it starts to dissolve. It gets smaller and smaller and smaller until it's just down to a molecule. And that means if I have a concentration, a lot of molecules in water, that can find each other, so they must be inside a cell. There's a chance that if they find each other over a long enough period of time, I get life making itself. So I want to see water as the solvent in which life is dissolved. There's another reason that you need water too. If you didn't have water inside your cells would look like this, and not this. Water holds your cells up. Now that's very important. So you have to see water as keeping the cell looking like that and not like that. Now, if we go back here, the cell. If I want to say what a living thing is, I need to say some of the characteristics, some of the things that all living things do. And one of those is to make new living things. That must be the most important thing that we can say about life. But here, I've got something which is not a living thing. It's got some DNA or something called RNA. And the next time you go to the Science Museum in Taichung, I want you to look for this. Now you'll see this as you go into the evolution hall before you go down to the dinosaurs. One of the first things that you see is this, a virus. Now a virus, there's no cell, no water, there's no chemistry, nothing changes. A virus can't make another virus by itself. It's just some molecules, like this, or this, if I could see down inside molecules, making more molecules, which are just the same. Now that means that it's part of atoms, it's part of molecules, that they will evolve, because as the virus makes more virus, some of those viruses will be different. It does have the laws of evolution. Now that's very important, to separate the virus away from the other living things, which are cells. They need water, and they also need energy. If If you don't have energy, nothing happens, nothing can change. And for a long time on the earth, the cells were using energy sources which were not the sun. When I was a little boy, the teacher told me all living things need sunshine. Well, that's wrong, very wrong. You can use anything as long as you get some energy out. Now that could be the heat from a volcano, it could be the heat from a chemical reaction. But I want you to see cells as something where things need to happen. And it always happens because we move these. This is the plus, this is the minus. It's the minus that moves around the cell and changes things. Now, if we look at the timeline, and I'm going to move on to about 3 billion years. Now, I've moved a billion years here, a much longer time than animals have been on the earth. And here, I put a colour on the board. These cells are green. These were the first cells that were using the sun. And they used the sun to change air and water into this. Now this is sugar. This is the battery for living things like you and me. We need to eat this so that we can drive the processes of life within our bodies. So this sugar, and this is the sugar that all animals and plants use, is really the basis of life. It's the building blocks. I've got to make everything from this. So I put this sugar down here, glucose. If you see these three letters, O-S-E, O's, well, that means sugar. Now, I teach the children a lot about sugar. We don't learn words like this. We just call this sugar number 1. It's the simplest sugar. C6H12O6. That's what these cells here were making. The first cells to make that were bacteria, just small cells. And here's a very nice picture of the bacteria that were doing that. These are blue-green algae, and the children look at blue-green algae a lot. They see how small they are compared to bigger green cells. But this was when life got going and speeded up. Because if you can make this from air and water, your energy supply suddenly becomes a much richer energy supply than if you're using the atmosphere or if you're living in a cave using warm water and chemistry. Now, if we start from here, we need water, we need the cell, we need energy. We can progress along the path of evolution. Really, what we're doing here, we're using energy and putting energy into the sugar. Now you can get the energy out of the sugar, and I'm going to show you, this is a very complicated chart. This is how every animal on the earth works. They start here with sugar number 1, glucose. Now that has to fall right down this chain here and change into this, and then it changes, and we have this energy cycle here which gives out water and CO2. So when I breathe out water and CO2, I'm getting energy, water and CO2 out, and I'm putting this sugar in. Now just to show you how this works, I've made this model here to show you that sugar or sunshine or anything else that you want to use for energy is really a battery. It makes the minus move. You need something to lift the minus up to the top of the chain and put it in. And when that happens, it falls down, and when it does so, it changes things. It makes things move. I get some energy out, but now it's stopped. So then I need to use my battery again. Now that could be sunshine, but I've got to lift it up to the top. And that's what we use this sugar for. Now, we don't eat this sugar like this. We eat this sugar in many, many different forms. It may be bread, it could be vegetables. Whatever we eat, we have to change it back into this sugar. Otherwise, we can't put just one of these in the right place here to make it work. If it isn't this sugar, it doesn't work. So it's always the same process, but that's how life works. Now, if we go back here and we look, let's move down the timeline of living things. It must be a cell, there must be water, there must be a supply of energy. Now we've got bacteria, small cells on the earth, making sugar using sunshine. Now cells change. They change all the time. And here we've got a long time for cells to change. These cells, bacteria, make more cells which are just the same. But because sometimes DNA will change, some of those cells will be different each time. And that means if cells are making sugar here, if other cells change, they can take the sugar. So we're going to separate all of living things into those that make sugar and those that take the sugar. So I've done that here. We'll start with bacteria because on the earth here there were just bacteria and nothing else. The sugar makers, some of them making sugar living in caves with no sunshine, some of them at the bottom of the ocean making sugar using the heat and the chemicals that come out of small volcanoes on the ocean floor. Most of them, the ones that we would recognize, living on the surface using the sunshine to drive our biological systems like this and make the sugar. But very, very quickly, other living things will change and come and take the sugar takers. Now, maybe around here, you can't be sure where because the fossil record of bacteria is so delicate and so small. Cells start to get bigger. Life changes and it becomes more complex. So from tiny, tiny little cells like this, which don't have DNA inside a nucleus like this, we start to get big cells. Cells that we would recognize, and cells which have behavior that we would recognize. Now the children look at this cell here down the microscope, and you would know this cell. Everybody sees pictures of amoeba in books, but the children here see real amoeba moving on a microscope slide and catching food, and they see it has senses. So it's a very, very complex living organism. I've drawn some bacteria here to show you how small bacteria are compared to the big cells. And the children look in the microscope, and on the same slide there will be big cells like this and the small bacteria cells like this, so they can compare the two. These are the two very famous ones that we like to show the children. This one here, this is a photograph that we took last year. It's called a paramecium. It's a very big cell. It moves very quickly. It catches its own food. It does have senses. And the children look in the microscope and see this touching things and moving in the other way. Now that means that here, cells are doing all the same things that animals do. They've got senses, they're catching food, they're moving, and very importantly, they're making more cells, but some of those cells would be different. They're keeping on changing and changing and changing. Now, if I move right over here and just look where we've come from, here on the earth, it's the first animal, or should I say, the first things that look like animals. Look at all this time on the earth that cells are evolving. Now, it's this long bit of time here which isn't in the science book because it's boring. You can't see dinosaurs and other things making themselves. It's not very exciting. But this is the important bit. This is the long period of deep time when the cells on the Earth changed into all the different kinds of cells that you need to make animals. Now you get a very good clue here, around 600 million years ago, of how animals made themselves. The cells start to live together. Now, if I show you this photograph, well, you say, that's a jellyfish, but you'd be wrong. This is not an animal. This is something called a siphonophore, and siphonophores are just colonies or groups of cells living together. It looks very like an animal, but this is 4 different groups of cells just living together. It can't move like a jellyfish. That's why it's got this bag, so it blows in the wind. So this is a very, very important clue of how living things change from cells into animals, multicellular. Now, from animals here, very, very quickly, on geological scales, that means on this timeline, we've come to having things like fish, and here, very, very quickly, we've got dinosaurs, and there's no people until right here, the last little bit. So it's this that we forget about. This is where evolution is really taking place, making all the different cells, which later will be used over here, to very quickly change into what we recognize as animals. And that can happen because DNA has a memory. If something is very successful, it keeps it. Now here, there would be animals like worms and animals like this. Now if I look at this, I can see there's no eyes, but it does have a shape, a fish shape, and it does have a head here with a mouth. And that means if you have a head, you also have left and right. And that means you have a sense of direction. You want to go one way. So we find that all animals on the earth have a head. One head. You don't find animals with 2 or 3, or if you do find animals with 2, it's just a one-off. They don't reproduce and become more successful. So when animals have started to have one head, that's the right amount of heads. And you'll find that 2 eyes is a very good number of eyes to have, because that does give you a sense of direction. If I've got more light coming into this eye than this eye, I know light is over here. I only need 2. So 2 is the right number. And the way that evolution works is that eyes would evolve in very, very different creatures, like an octopus or a fish. And they evolved separately, and they both have 2 eyes. So that's how evolution works. If 2 is the right number, that's the number you get. Now, this is our first ancestor. It's the first animal which has a line down here which carries electricity from the head down the body, and you've got muscles so that you can move using that electricity. And we find fossils of animals like this right back here on the earth. Before there's fossils of animals which have bones or eyes or anything else that we recognize. So really, I can put this one right over here. This is the first thing that we find which has something going from the head down into the body with muscles so that you can move. It's got a mouth, it's food in and food out, and that pattern is the pattern which is going to evolve and keep changing and changing and changing very quickly in geological terms into things that we recognize. Now, this is called a lancelet, and they're still on the earth today. We find fossils of animals that we call picayer, which look just the same as this. It's really a worm. It's a very advanced worm. And there are some worms now that have eyes on the earth. So they have left and right. They have 2 eyes. animals like this very quickly change into animals like fish. The very first fish would be very, very simple. They didn't have fins, but they did have bones. If you have bones, then you're strong. And if you're swimming in water and you want to move the water, you need something strong inside. You need bones to give you structure. And what you will find is that when we look at the pattern of a fish, I see all the same things that people have. Now that seems a very strange thing to say. I don't look like a fish. But this is something that, because we're people, we miss. A fish has one head, two eyes, a mouth, bones, a heart, blood, and it's the same pattern as us. Now it's very easy not to see that. You see everything that's different, but I really do want to look at everything that's the same. Because if you were an alien and came down to the earth, the thing you would notice is that all the animals after the fish on the land are the same pattern. And if you just use the same pattern and keep changing it, the evolution can happen very, very quickly. And if you go out to Dajia in Taiwan, you can see a fish out of water, walking on the mud and breathing air. And that fish is changing now into something else. We can't see it because it takes so long for animals to change. But I want to open the children's eyes so that when they look at something, they don't see it as an animal like a sea lion. They see it as something that's changing into something else. It's got a head, like a dog, feet, which are like the tail of a dolphin. Now if I show you this, it's easy for you to understand. You can see it. But if nobody shows the children pictures like this, then it's very difficult to understand. Now the next lesson, when they get to grade 2, is how the animals change here. Now that's all we're going to do this week, so I really hope I've opened your eyes into how we do science here. And I'm going to say a special thanks to Sophie for helping with this. So we'll see you next semester, and I really hope that your children enjoy my science. Bye-bye now.